A common misconception about black holes is that they are incredibly dense. They are actually formed from dense objects, collapsed stars, but the black hole itself is nothing. Consider our sun, which is about 1.5 million kilometers in diameter. If we shrink the sun to a smaller scale, it would have to be less than 6 kilometers across to contain all of its mass. At this point, the sun continues to collapse, leaving no solid surface or remnants of its original material. It becomes a region of empty space. Approaching a black hole, one may not even realize the impending catastrophe. Therefore, it is more correct to perceive a black hole as a place, not as a thing. Let's take a few minutes to define the concept of curved space-time. Einstein's equations explain how space and time affect matter and energy. If you throw any object around the Earth, it flies in a curved path, forming an arc. If you give it enough velocity, you can put it into orbit. Think of the International Space Station, for example. The International Space Station is launched at 17,500 miles per hour, which puts it on a curvilinear trajectory in which it is essentially free-falling around the Earth. Once in this orbit, the engines are turned off, and it continues on a perfect circle. This orbit demonstrates the curvature of outer space around our planet. These orbital trajectories, or arcs, are the curves of space-time. If you were to unwittingly approach a black hole while exploring space, you could get very close to it without immediately sensing the impending danger. A black hole acts like a gravitational lens, distorting light from the surrounding space through its gravitational curvature. However, if you belatedly realized your proximity to a black hole and desperately wanted to escape, you would face significant fuel supply problems. Launching objects far from massive gravity sources is expensive and difficult. Launching spacecraft from Earth is an extremely expensive endeavor that requires a tremendous amount of energy. If you carelessly get too close to a black hole, no fuel in the spacecraft's tank will be enough to escape. As you approach a black hole, you not only realize that space is curved, but you also observe a time warp, a phenomenon known as time dilation. This means that the intervals between clock ticking, breathing, and even thoughts seem to slow down compared to a person far away from the black hole. Although your perception of time remains normal due to synchronization with the clock, observers at a great distance will perceive it as slowed down. As you approach the black hole's shadow from a distance, it will seem as if your clock has stopped completely. Moreover, as you approach the black hole, the available orbital trajectories for objects become smaller and smaller, and eventually, you'll get so close that there won't be a single turn leading outward. All paths lead inward, defining a shadowy area around the collapsed object. This shadow marks the boundary known as the event horizon, beyond which no information can escape. Even light itself cannot break free. It may surprise some people to learn that the larger the black hole, the longer you can safely stay in its vicinity. If you cross the event horizon of a black hole, you could watch the evolution of the galaxy behind you, take notes, write poetry, and experience a profound sense of existential dread. In the case of the largest conceivable black hole, you could do this for about a year, provided you had the necessary supplies to sustain life before suffering the inevitable fate at the center. Our understanding of black holes leads to the mathematical prediction of a singularity, a region in space-time whose curvature responds to infinite density. All matter is compressed so strongly that it creates an infinite curvature of space-time. As you strive toward this singularity, which cannot be avoided, you will notice that space forces the atoms of your body closer to this singularity. It is also trying to pull you apart. You will suddenly notice that the curvature of space at your feet is greater than at your head. You will feel your legs pulling away. This process will continue until you are torn apart. Eventually, even the atoms themselves will be torn apart into their fundamental quantum components. As you approach the singularity, this process culminates, and in a finite amount of time, you reach the end. If the singularity does exist, then it would seem that your quantum particles have completely left the universe, and essentially ceased to exist. This concept is deeply disturbing, not only on a metaphysical level, but also from the perspective of a scientist or physicist. This scenario challenges some of our fundamental principles. Our basic principles may need to be reevaluated, and we may have to reconcile ourselves to the idea that things fall out of the universe and cease to exist. On the other hand, these principles may remain inviolable, allowing us to use them as tools to understand how to redefine the ultimate fate of material trapped in a black hole. Black holes may play a key role in the narrative, tracing our path from the Big Bang to the origin of life. Moreover, we are orbiting a supermassive black hole in our Milky Way galaxy, raising the possibility that one day, we too will fall into a black hole. This could be the ultimate fate of these atoms in the solar system. In light of these considerations, it is worth considering that we all live on the same planet, are descendants of the universe, and may eventually converge at the center of a black hole.